We are going to continue with paper 2 of the YTSS Prelim 2014 for the pure physics subject. Okay, first question is your kinematic question. You are given a VT graph. So on the VT graph, just label the points so that it is easier for you when you are calculating the gradient. So the first question asks you about acceleration, and you need to know that the acceleration is represented by the gradient of a VT graph. Put in the value and you'll be able to get the acceleration of the different segment of the graph. So please remember that acceleration unit is meter per second squared. Okay. Now the second part of this question, part B, is asking why the acceleration are different. So if you look at the graph here, you see that the gradient here and the gradient here are different, and they are asking you why is it that in QR the gradient is actually lower than the PQ. Now, if you read about the context of the question, basically what happened is that you have a block. It is given an initial push. It will go up to the highest point and then it's like to slide down again. Now, if you draw out the forces acting on this box, you will definitely have the weight of the box, which is the gravitational force acting on the block. And because the block here is moving up, so friction will be opposing the motion. Okay, so what is going on here is actually corresponding to PQ when the box is actually going up. Okay, why do I know that PQ is going up? Because the velocity is slowing down, and at one point it starts to turn. So at this point when velocity is 0 is actually the maximum height, and that is when the direction of motion starts to change. Okay, so after that, the QR part, the QR segment is actually describing the block sliding down. So the question is asking you, why is it that when the block is going up, it is decelerating faster than when the block is moving down? Why is there a difference in acceleration? The reason is because if you look at this force factor, you can see that they will have a combined effect, right? They are actually, if you look at, if you imagine this slope boundary is the x-axis, is the horizontal. So if you look at it like this, okay, imagine that that is the horizontal. So these two forces will actually will have a component whereby they can act together, is effect. So this one will produce a larger deceleration. Therefore, your gradient here will be steep. But if you look at this, it is as if that the frictional force is resisting the gravity pulling the block down. So because of that, the gravitational pull will be slightly weaker, and it is being weakened by the friction, which is opposing the motion. So therefore, the combined effect of these two will be lower than this. Okay, the frictional force is actually slowing the block from being pulled down by the gravity. So therefore, you will see that the slope here is gentler. Okay, so that is the concept behind. So how are you going to phrase it in English? Now, you have to say that when the box is going up the slope, both the gravitational and frictional force are acting against the box motion. So this will produce a large deceleration. And when the box is going downwards, the frictional force is actually against the motion, but the gravitational force is not. Actually, the gravitational force is the one that is responsible for pulling the block down. But friction is actually trying to resist that motion. So therefore, the combined effect of it will be a lower deceleration. So hence, the two acceleration between a PQ and QR cannot be the same. They must be different. Okay, let's look at part C. Part C, they are asked you to find the greatest distance. So like I said in part B, the greatest distance will be from the start all the way till the block begin to change its direction. So that is from this part all the way till when it starts to change direction, which is this point. So the distance traveled is the area under this part, so it is a triangle. So put in the right value, the correct formula to find the area of triangle, you get the correct answer. Remember the unit is in meter. Okay, what is the kinetic energy of the box when it is projected up the plane? So use the correct formula and state it. Always state the formula first. So K equals to half mv square. what is this V? This V is the initial velocity. So if you look at the graph, the initial velocity is 40. So go and put 40 in, you get the correct value, 96,000 joules. Okay, then for your part E, they are asking you again for kinetic energy when it returns. So if you look at the graph, use K equals to half mv squared. When it returns, the velocity, so what happens is that when it reaches this point, velocity is 0, then it will get accelerated down the slope. So when it comes back to the same point, your velocity is negative 20 because now the velocity vector is pointing down. That's why the negative sign. So anyway, you are finding Ke, so whether positive, negative, it doesn't matter because the V is going to get squared. So you get the Ke equals to 2400. So by comparing the part D and part E, you realize that the Ke is different. Then you may ask, then how about PE? Now the thing about this is that for part D, you are finding the initial Ke here. Yes, there could be some PE, but the PE will be for this height. Now for part E, you are finding the Ke of the box when it reaches the exact same position as the initial part. So therefore, the PE will be still the same H. So therefore, you do not need to account for the difference in PE. They are at the same height, just that they have different speed. So the question is asking you, why is there a difference in kinetic energy? Well, the difference in terms of kinetic energy is because some of the energy is being lost in the form of heat due to friction, because just now we mentioned there's this frictional force, right? And frictional force will generate heat, and heat will cause energy loss. So the difference is the energy loss. So now here they are asking you to find the frictional force. So you know that the heat loss is equals to the difference in terms of the Ke. So here you can find the heat loss. And you know that this energy loss is due to the work done against friction. So work done against friction is just equals to the frictional force multiplied by the distance that it has moved. And from your part C, you know that the distance that the block moved is 100. So it's 100 up and 100 down. So in a total, you have 200 meter. So from here, you know that, okay, the work done against friction is 200 multiplied by the frictional force. So at this point, I still do not know what is my frictional force, so I give it an algebra of F. So down here, I know that, okay, this 72,000 joules will be equal to the work done against the friction. So I equate the two of them together, and eventually I can find out what is my F. So that is 360. Okay, question 2 is about your hydraulic jack combined with a lever here, which I think the question is going to talk about moment. Okay, so let's try. So yes, it's going to be about moment. So they say that you can ignore the mass of the lever and just focus on the forces producing the moment. So you have moment on the lever. From the lever must be equals to the moment from the piston. Why I'm saying that? If you look here, there's a force here. You can ignore the gravitational force pulling onto the lever, and there will be a force on the piston as well. So the force on the piston is definitely going down. So by Newton's third law, the force from lever to piston is down. So Newton's third law says that the direction will be opposite. So therefore the piston on the lever will be up. So therefore the force on the lever, this one, okay, will be clockwise, and the force from the piston on the lever will be going up, which will give you a turning moment, a clockwise moment. Okay, so therefore you can use this expression. So express the moment in terms of force and this perpendicular distance. Substitute the correct value. The force on the lever is 40. Distance from the force to the pivot is 0.8. Force on the piston you do not know, but you know that the piston is from 0.2 from the pivot. So solve this equation, you'll be able to find the force on the piston. Okay, for part B, you are asked to calculate the pressure. Pressure is just equals to force over area. So once you have that, you can get the answer. Remember, unit is Pascal. Okay, down here for hydraulic jack, one of the basic working principle is that the pressure at A must be equals to pressure at B. Okay, so since you already find out what is the pressure at A, you can express the pressure at B in terms of force at B over area of B. So put in the right value, do a bit of manipulation, you will be able to find out that the FB is equals to 24000 Newton. Then you are asked to find out what is the distance traveled. So the second working principle of a hydraulic jack is the conservation of energy, meaning that the work done at A must be equals to the work done at B. And the work done is basically equals to F times the distance moved in the direction of the force. Okay, so you have already found out what is your FA, you have already found out from what is your FB. What you need to be very careful is that this is in cm. So change it into meter, solve your equation, you will be able to get your distance at A in terms of meter. Okay, now if you forget to change this into meter, then your final answer will be in cm. Okay, but it is always a good practice to change the value into their SI unit. Okay, question 3. Question 3 is on wave. Down here that you are asked to draw the wave front from F. So make sure that this line and this line is parallel to each other. It should be fine. Okay, define wave front. Refer to your textbook for the definition. Okay, this is the part that I have just mentioned. Make sure it's parallel. Explain in which medium, I or R, the wave has higher speed. So basically higher speed would means that your optical density is low, so you will have low optical density. So basically you want to find out between I and R which one has lower optical density, and it is pretty straightforward. So if you look here, the wavelength in I is big, right? So the wavelength of I is bigger than the wavelength of R. This is smaller. Now, when you are sending wave out, the frequency of the wave is controlled by the source. How fast you vibrate, okay, how frequent you vibrate. The frequency will not change by the medium, right? The medium can only change the wavelength, but the frequency will be the same. So you know that the frequency of I and the frequency of R, they are the same. So with this knowledge, you can use the formula V equals to F lambda, since the frequency is the same. So when you have something the same and this guy become big, then your velocity here will become big, right? And you want to find the higher speed. So therefore, the lambda here, you want to have the lambda of I. So now that you understand the concept, let's put it into words. Okay, so I, the distance between the wavefront is larger, but this is not such a good explanation. You are just stating your observation. So how do you explain? So in I, okay, the wavelength is longer, okay, and since F is not affected by the medium, the F in I will be equals to the F in A. So by V equals to F lambda, V in I will be larger because the lambda in I is larger. Okay? You can quote formulas in your explanation, no issue about that. Okay, now you are asking to find the ratio of the speed between I and R. So like just now how I explained, the speed in I and R is given by V equals to F lambda. So you have Fi lambda I, Fr lambda R here. But because the frequency is controlled, is only dependent, the frequency is only determined by the source that produces the wave. Yeah. So the F here and the F here will be the same. Basically, they can then that be cancelled off because they are the same. So you are left with lambda I and lambda R. And I think they tell you that you can make measurements from the diagram. So put your ruler okay, on the graph. So how do you find wavelength from wavefront? Basically, the wavelength is the perpendicular distance, okay, between two wavefronts. So this one will give you the lambda I, and this one here will give you the lambda R. So go and measure it. Okay, once you measure it, put it right here, you will get the answer. Okay, ratio doesn't have unit. Okay, part E. Part E, they give you a velocity and time graph. Okay. Okay, so they are asking you, how do you know that this is oscillating? Now, I know that the answer key is saying that, oh, okay, there is a turning point because V equals to 0 at these points, right? This is V equals to 0, this V equals to 0, this V equals to 0, this V equals to 0. So meaning that the particle turns at every about 1.5 milliseconds. But this does not mean that it is oscillating, right? Because imagine now I move here, I turn, I move here. Okay, I do slow. I move here, I stop, I turn. I move here, I stop, I turn. But this time I move here, I stop, I turn. I move here, I stop, I turn. Move here, I stop, I turn. Is this an oscillation? No, right? It is no regular pattern. It is just turning and turning. So what is the key characteristic of an oscillation? The key characteristic of an oscillation is that when my pen oscillates, it will go left by some amount, go right by exactly the same amount, and then this process will repeat. So what you are looking at is not that the particle will turn, but rather the distance it covers when it turns, right? So if we are talking about the distance it covers when it turns, we are actually looking at the area underneath the line, right? The displacement. The displacement must be the same. Yeah. So now that you have this concept, put it in words. So first, define what is an oscillation. So an oscillation refers to a motion pattern which the particle will vibrate about an equilibrium position with equal displacement to either side. So from the graph, the area under the graph above and below the time axis is the same. So this indicates that the displacement to either side is the same, and hence it is an oscillation. Okay, let's move on to part 2. You are asked to find the frequency of the oscillation. Now, from the graph. So if you look at the graph, this is very different from the graph that you encounter, because the graph that you encounter in the textbook or TYS is usually displacement versus time, if not displacement versus distance. But now you are given velocity versus time. So how do you find period in this graph? Would it be this distance, and how many waves should I count? So you have to really interpret this graph from the first principle. Now, if you look at a graph, what is the definition of period? Is one full oscillation, right? Period is one full oscillation. So look at, imagine that you have a normal graph. Let's say you start from the peak. It goes down, it goes bottom, it goes back up. Ding dong. This is the period for one oscillation. So one oscillation starts from the peak, goes down, back to the peak. So if you look at this is one full oscillation, right, in terms of movement. But how about in terms of velocity? Now, it starts at the top point, right? So at this point, it is turning. So V equals to 0, go by another turning point, V equals to 0, go by another turning point, V equals to 0. So in one full oscillation, how many times will velocity equals to 0? 3 times. 1, 2, 3. So look at this graph. This is 1 time when the velocity is 0, 2 times when velocity is equals to 0, 3 times velocity equals to 0. So you know that at this time, it is where the one complete oscillation has happened, and it happens at the 3rd second. So from this graph, you can also tell that the period of one oscillation is 3 milliseconds. Be very okay, read here is milliseconds. So therefore, down here you can then put the period is 3 milliseconds, change it to seconds before you use the F equals to 1 over T formula because it only accepts SI unit. So you get 33Hz. Okay, then after that you are supposed to mark on the graph with a letter M one time at which the particle is at maximum displacement. So maximum displacement, good. If you look at the thing that I just drew, this is the equilibrium position, right? When the particle goes up, maximum displacement, back to the equilibrium position, goes the other way, back into the equilibrium position, goes the other way. So when is the maximum displacement you get? It will be where? Here? Here? Or here? It will be here, right? When V equals to 0. So where is that maximum point? Is it at V equals to 0? Now I want you to think. What is the maximum displacement? Maximum displacement is when the V is 0 again, right? So therefore you will stop at where? You want the displacement travel from V equals to 0 to whereby it is at the equilibrium position, right? This is the maximum displacement you want, right? So the maximum displacement, let's write it down so that you can see it. So the maximum displacement, it is when V equals to 0 because it is turning all the way till it passes the equilibrium position, right? And what is the V when it passes through the equilibrium position? It will be at its maximum, right? So on this graph, where is the displacement, the maximum displacement? It will be when V equals to 0 all the way till velocity is maximum. So this represents the maximum displacement. This portion here, this represents the maximum displacement. Okay, so this is your M or X? M. So mark this with a M. And the reason is you have to define the maximum displacement. Maximum displacement is from here to here. So it is when V equals to 0 all the way to V equals to max. This line here is V equals to max. This line here is also the equilibrium position. Okay, so you need to have that concept. Okay, question 4. Question 4 is very easy. It is to give you marks. So down here, name component P and Q, refer to the textbook, is your EM spectrum. Just read it. Give 2 reasons why it is being placed together. Okay, I'm good enough. I will just write it down. They are transverse wave. They're the same type of wave. They travel at the same speed in vacuum. Okay, you must state that it is in vacuum. If they are not in vacuum, they will be at different speed. Okay, I dropped my cap. Suggest what is the likely value of the wavelength. Anything between this will do. Then after that, you are supposed to calculate the distance between Sun and Earth. Now please be very careful because the velocity you are using is meter per second. So therefore your time here is in minute. So remember to change it into seconds. You will be able to get the distance from Sun to Earth in meters. Okay. Okay, for question 5 is pretty tricky. Now you are given this whole bunch of data and then you are asked to find the focal length. So don't worry, we'll do it step by step. They already tell you that M is 1.5, so let's stick to it. Now what you want to do is you want to draw out as much information as you can from this table. So when M is equals to 1.5, you know your V, your image distance. So let's do it now. So okay, let's draw the center line and then put our lens somewhere here. Okay, now because first information you're going to use is that at m is equals to 1.5, you know that your V is on the table 275. So down here is 275 mm, right? And you don't have such a big line to get 27.5, so this is about 27.5 cm, right? So let us create a scale, because I cannot have everything here, so let's make a scale. So 1 cm on my diagram would be equal to 10 cm or 5 cm from the data. So meaning that this 27.5 cm on my diagram will become about 5.5 cm. So it's a scale diagram. So 5.5 cm. Oh, okay, pretty far. 5.5 will be somewhere here. So I know at this line, this is where my image will form. Now the second information that I need to make use is that I know that m is actually equals to a ratio. So this ratio is height of image over height of object. So I know that this is height of image and this is height of object. And I know that they are related by this. So let us call it hi over ho. Okay. Now, since it is my diagram, I can express. Let's express this into a linear form. So this can be expressed as this, right? Right. Since it is my diagram, I can simply let my HO be 1, and this would make my HI be 1.5. Fair enough. I'm the one doing the experiment, right? I choose it. So I would choose an image of 1.5 cm on my diagram. So I'm going to measure 1.5 cm on my diagram. Right, and I know that when I have a 1.5 cm image, I'm going to get a 1 cm object. But I do not know where is my object along this line. I only know that it is going to be 1 cm height. So I'm going to draw a reference line of 1 cm height. So let's draw this carefully. So I know that this will be 1 cm height. Okay, then let's draw the light ray. Okay, I have used up all the information. I know that my first light ray will be from the tip of my image to the optical center. So I'm going to cross this. And ta-da! This line, this ray of light must be from the image tip to my optical center to my object tip. And my object has to be 1 cm tall, right? So therefore, I find my object. This will be my object. Liquid away this line. Draw the ray arrows. And then now I need to determine my focal length. But since now I have my object, it is pretty easy. Just draw this. Cuts to here. This will be my focal length. Okay, my dog wants to go out of my room, so I have to open the door. Yeah, Daddy, let's go. Don't go out, huh? Don't go out? No? No? Okay. Okay, now he doesn't want to go out. Okay, anyway, let's continue. So now we have our F. Measure the F, which is around 2.25. Okay, so this F is around 2.25 cm on my diagram. That means I have to multiply it by 5 so that I can get the actual dimension, because that is my scale. So I will get 11.25, so therefore 11.25 cm. Okay, that's how you solve this. how is the image affected by covering half the lens? Now this one you need to have this basic concept. Actually, light rays are going out in all direction, okay, from this object, all direction, okay, meaning that even though you have covered up half of this, okay, the light ray is still going, like for example, it is going to go here, you know, and then focus on here. It is going to go here to here, okay, it's going all direction. They're all going to focus on one point. So even though if you cover the top, the bottom lens is still going to focus, okay, the object's light onto where the image is. That means the position of the image, the size of the image is not affected. Okay, so down here what you can write is that the position and size of the image are not affected. So you will be asking me, hey, so no effect? Is that possible? But the thing is that if you cover up this half of the lens, you are effectively blocking all the light, okay, from the top. So what do you think about the intensity of the light here? It will be less, right? So less intensity means that your image will be brighter or dimmer? Yes, it will be dimmer. So the image will only be dimmer. Okay, now next thing, when the lens is moved closer and closer to the object at one position, the image can no longer be formed on the screen. Okay, for part C, I think it is too simple. Okay, what happens is that when you are moving the lens towards the object, you are actually it's the same thing. You can think of it in the same way as you are moving the object closer and closer to the lens. Okay, and when this happens, once the object is on 1f from the lens, you will have the image at infinity. And when the object continues to move nearer to the lens, you are actually below 1f, and below 1f you will get a virtual image formed on the same side of the object. You become like a magnifying glass. Okay, so what you need to write here is very simple. So when your object is at one focal length from the lens, okay, the image form will be at infinity. So you already lost the image. And when the object continues to move closer to the lens, okay, below 1f, okay, the image will be virtual and forms on the left hand side of the lens. So hence the image on the screen will be lost once the object is at 1f. Okay, so it is pretty straightforward.